September 11th, 2025. A quiet alert flickered across the SOHO mission's data feed, a faint shifting blur in the SWAN camera buried in the solar haze. At first it looked like background noise, but within hours automated analysis confirmed something else entirely. A massive object glowing with volatile gases had just swept past the sun, and no one on Earth had seen it coming. For months, ground-based observatories had watched 3i Atlas dominate the headlines, the interstellar visitor everyone was tracking. But behind that distraction, another body slipped into our system unnoticed. Designated C 2025 R2, SWAN, it's not an asteroid, not interstellar, but a long-period comet of immense size that somehow evaded every major sky survey. When it was finally detected, it had already completed its closest approach to the Sun, just 0.503 astronomical units away, and was heading toward Earth's orbital zone. Now, in mid-October, its trajectory places it only 0.2606 astronomical units from Earth, close enough to raise questions no one expected to ask this week. How could something this large go unseen until it was already here? And more importantly, what does its strange, unstable behaviour mean for what might be following it? This is not another 3i Atlas story. This is the one that slipped through the blind spot, and it's still coming. It began in silence. While telescopes worldwide tracked familiar objects across clear autumn skies, something vast moved beneath their notice, a body reflecting sunlight just enough to hide in it. Long-period comet C 2025 R2, SWAN, didn't sneak into the solar system. It blinded its way in, approaching from the sunward direction where every optical survey fails. For months, automated systems like Pan-STARRS, ATL-AS, and Catalina had scanned the dark half of the sky, searching for faint inbound comets beyond Jupiter. None flagged this one. The geometry was impossible. Any object coming from that direction was effectively invisible, arriving from the day side where even the best instruments are powerless against solar glare, and so the comet slipped through the detection net, unseen, unlogged, unpredicted, until it had already reached the heart of the solar system. When the SWAN instrument aboard the SOHO spacecraft picked up the faint ultraviolet glow of hydrogen on September 11th, the realization hit quickly. This wasn't a background artifact or a passing flare. It was a hydrogen coma, the signature of an active comet releasing water vapor and volatile gas. The timestamp was chilling. The object had just passed perihelion, its closest approach to the Sun, one day earlier at 0.503 astronomical units. It had been there, erupting, while the world looked elsewhere. The first orbit calculations painted a strange picture. This was no interstellar visitor like 3i Atlas. Its path tied it to the distant Oort cloud, meaning it had likely not visited the inner solar system for millions of years. But the data also suggested something more troubling. Its inclination and eccentricity placed its inbound leg deep inside the zone no ground-based survey can monitor. It had approached from behind the Sun, the one place no one was looking. That realization changed the tone among astronomers overnight. The discovery wasn't alarming because of a threat of impact. The orbit was safe. It was alarming because it shouldn't have been possible. In an era of skywide monitoring, how could an object of this scale, outgassing this violently, remain invisible until after its closest solar pass? The numbers tell the story. SWAN's brightness increased by nearly 5 magnitudes in less than 48 hours, an eruption equivalent to a 100-fold increase in luminosity. That spike wasn't slow, it was explosive. By the time amateur astronomers tried to image it, the comet was already brightening beyond model predictions, expanding a green coma dominated by diatomic carbon, a chemical hallmark of energetic sublimation and fragmentation. This wasn't just a quiet comet. It was a volatile one, shedding mass, venting energy, and refusing to stabilize. And that volatility brings new problems. The orbital uncertainty, the difference between where it should be and where it's observed, began to grow, not by kilometers but by tens of thousands. The cause? Non-gravitational forces, likely from asymmetric jets of gas. That meant its nucleus was rotating unevenly, venting in bursts, each thrust altering its trajectory. Within days of its discovery, the European Space Agency's data analysts noted that SWAN's predicted position didn't match its observed arc. The drift was subtle, but real. It suggested that the comet's mass distribution was uneven, a possible sign of fragmentation. In astronomical terms, this is where the story turns. A comet that large, active, and unstable doesn't just pass through quietly. It leaves trails, fragments, dust, micrometeoroids, debris streams that can intersect planetary orbits long after the nucleus has moved on. That's why the late detection matters, because by the time it was found, its path had already crossed key orbital corridors used by satellites and probes. For the agencies responsible for spacecraft operations, the focus now shifted from discovery to defense. The object itself posed no direct risk, but what it left behind might. And yet, the real mystery isn't its chemistry or its mass loss. It's the silence that preceded it. The comet didn't appear suddenly. Our instruments simply weren't looking in the right direction. A gap in surveillance, a literal blind spot facing the sun, had let it slip through. That blind spot, that dark wedge of sky hidden by brilliance, extends more than 15 degrees from the sun's edge, an area no telescope on Earth can observe without damage. And anything entering from that zone can go unseen until it's already past perihelion. See 2025. R2 wasn't just an astronomical event. It was a reminder that even with global monitoring, even with space-based networks, the sun itself can still shield an incoming object from every eye on Earth. And that realization would lead to a larger question, one that goes beyond this comet. Because if this one could hide there, what else could? Every telescope on Earth has an enemy: daylight. The sun's brilliance floods our atmosphere with scattered light, washing out faint signals and drowning the sky in blue. For astronomers, this means a permanent loss of vision, a wedge of space around the sun that cannot be watched directly. Within that wedge, an object can cross millions of kilometers unseen. See 2025, R2 emerged from precisely that zone. Its inbound path came from a low solar elongation, meaning it was visible only during the day, when no optical or infrared telescope on the ground could safely point near it. Surveys like Pan-STARRS and Atlas, scanning the night sky every hour, are blind to the region within about 15 to 20 degrees of the sun's glare. That's roughly 1/6 of the sky, a massive blind spot. And this is where the comet hid. The reason is both simple and unforgiving. Sunlight overpowers faint reflected light by billions of times. Even a bright comet tail cannot compete. The detectors saturate instantly, the sensors overload. In that zone, comets, asteroids, and even near-Earth objects can slip through completely undetected until they re-emerge post-perihelion, already changing direction, already beyond the sun. That's exactly what happened on September 11th, 2025. The Solar and Heliospheric Observatory, orbiting 1.5 million kilometers from Earth, caught what the ground could not. Its SWAN instrument doesn't use visible light. It detects hydrogen Lyman alpha emissions, ultraviolet radiation invisible to human eyes. It's designed to map the solar wind, not hunt comets. Yet this time it caught a massive outgassing plume. The hydrogen signature revealed the unmistakable presence of a volatile nucleus, already venting water vapor into space. And here's the unsettling part. The comet had already completed its closest solar approach the day before. It had passed within 0.503 astronomical units of the sun, flaring, erupting, and brightening, completely unobserved. By the time it appeared in SWAN's ultraviolet field, it was outbound, already receding. That timing raised alarms in the astronomical community, because if SWAN hadn't been operating, no one would have known. We might not have detected the object until late October, or not at all. The incident reignited an old debate, the sunward detection gap. It's not new. Nearly every decade, an object emerges unexpectedly from the solar region. The 2002 Oort cloud comet NEAT, the 2010 solar grazing fragment Lovejoy, and 2018's C2018 V1, Maholtz Fujikawa Iwamoto, all appeared suddenly from the daylight side. Each one exposed the same vulnerability. Our planet's telescopes see everything except what's in front of the sun. The geometry is brutal. Earth's orbit lies in the ecliptic plane. Comets from the outer solar system often arrive on steep sunward inclinations. When they approach from above or below the plane, they move into the sun's glare before any instrument can get a clean view. Even infrared space telescopes like NEOWISE, which can peer closer to the solar direction, struggle when the target is still inbound. To make matters worse, this region isn't just bright, it's unstable. The sun's corona emits flares, plasma, and high-energy radiation that interfere with sensors. Observations are further complicated by solar storms and cosmic ray noise. Every image has to be filtered, cleaned, and cross-referenced against transient artifacts, a process that takes time. And time is what astronomers didn't have when R2 passed perihelion. When the object's orbit was first reconstructed from SWAN's data, one statistic stood out. Its perihelion passage occurred just 24 hours before discovery. In other words, humanity detected it a full day too late to study its solar encounter. We don't know how it reacted to the heat, how much material it lost, or whether fragments were ejected. Those critical hours are blank. The implications go beyond a single comet. If something smaller, say a rock tens of meters wide, followed a similar trajectory, we'd have virtually no warning before it entered Earth's orbital zone. The Chelyabinsk meteor in 2013 arrived from roughly the same direction from the sun's glare and went unseen until it exploded over Russia. That's why astronomers now call this region the solar blind cone. It's not hypothetical, it's measurable, predictable, and permanent, and for now, it's a vulnerability no technology has closed. But R2's arrival reopens an uncomfortable truth. The sun doesn't just power life on Earth, it hides the universe from us. And while this comet won't hit our planet, its passage through that invisible corridor is a live demonstration of how something far smaller and faster could. Yet even after detection, the questions didn't stop. Because when telescopes finally turned toward it in late September, what they saw didn't match expectations. The object was not just active, it was unstable, flickering, and chemically strange. The sun's glare had hidden it. But now that it was visible, the mystery deepened. The first clear image came from a machine that was never meant to find comets. SOHO's SWAN instrument, short for solar wind, AN isotropies, is a small ultraviolet imager used to track how the solar wind spreads hydrogen throughout interplanetary space. Its primary mission is to study the sun's interaction with the solar system. But on September 11th, 2025, it caught something that didn't belong. At 8:42 UTC, a faint asymmetrical glow appeared in a sequence of ultraviolet frames. To most analysts, it looked like noise, a spurious hotspot in a sea of solar interference. But the software's background subtraction algorithm flagged it twice. The shape was shifting, and its centroid was drifting outward, behavior inconsistent with cosmic rays or instrumental noise. Within hours, the anomaly had moved. It wasn't fixed in the sky. It was following an outbound vector from near the sun, showing acceleration consistent with an object under solar radiation pressure. That alone was enough to classify it as a likely comet. The confirmation came fast. The hydrogen cloud it emitted wasn't uniform. It pulsed. Evidence of active outgassing, meaning the object was venting water vapor into space. SWAN's sensitivity to hydrogen allowed researchers to calculate production rates, about 40 kilograms of water per second, a powerful level of activity for a body so newly discovered. That number stunned observers. If the nucleus was small, the surface would be boiling. If it were large, then the outgassing was intense, far greater than models predicted for a comet at that distance from the sun. The signal implied rapid sublimation of ices beneath a fragile crust, a nucleus under stress, releasing energy unevenly. At first, the discovery went unnoticed by the public. The astronomical telegrams didn't make headlines. They rarely do. But inside the minor planet community, message boards and private servers lit up overnight. The data from SWAN didn't just show a comet, it showed a late discovery, one that had already peaked in brightness before anyone knew it existed. Calculations from the Minor Planet Center placed its perihelion at September 10th, 0.43 UT, at a distance of 0.503 AU. That's roughly halfway between the Sun and Earth, a region astronomers call the warm zone, where many comets either fragment or flare. C2, 025R2 had completed that pass before any human observation. Every image we have of it is post-perihelion, after it already endured its most violent transformation. The orbit fit the pattern of a long-period comet, a near-parabolic trajectory, inbound from the Oort cloud, looping around the Sun once every several million years. But one value didn't fit. The eccentricity wasn't precisely 1. That hinted at small, non-gravitational accelerations, meaning jets were pushing it off its purely gravitational path. That's when the talk turned to asymmetry. If a comet vents more strongly on one side, it experiences thrust, a subtle, persistent shove that shifts its course. This is how non-gravitational drift happens, and in the case of C2025 R2, it was measurable within days of discovery. Observers noted the uncertainty region expanding faster than expected. The comet's predicted path began to diverge from observations by tens of thousands of kilometres. Not enough to threaten Earth, but enough to complicate trajectory forecasts. That's why NASA's JPL quickly added it to their daily orbit refinement list, a roster reserved for unstable or evolving bodies. By September 15th, ground-based telescopes finally managed to image the comet at dawn twilight, low over the eastern horizon. The early photographs revealed a diffuse, greenish coma spreading more than 200,000 kilometres across, about half the distance between Earth and the Moon. Spectroscopic data confirmed the cause: C2, diatomic carbon, emission bands dominating the visible spectrum, the classic source of that eerie green hue. Diatomic carbon doesn't survive long in sunlight, it dissociates quickly. That meant the green colour was constantly being renewed, replenished by active jets near the nucleus. But curiously, the images showed no sharply defined tail, only a broad fan of haze. It suggested that the nucleus wasn't stable enough to sustain a focused jet. The material was dispersing in all directions. That was the first clue that something unusual was happening internally. By late September, as the comet receded from the Sun, it did something unexpected. It brightened again. Most comets fade steadily after perihelion as their volatile ices depleted. R2 didn't. Its light curve showed secondary spikes, abrupt surges of several magnitudes within hours. Astronomers called these outbursts, sudden releases of trapped gas and dust that momentarily inflate the coma before it dissipates. This was not a quiet, predictable object. It was chaotic. And in that chaos lay the deeper worry. Instability means fragmentation. When comets outburst repeatedly, the mechanical stress can tear them apart. It happened to Comet 73P Schwassmann-Wachmann in 2006, to Comet C2019Y4 Atlas in 2020, and to dozens more before them. Each one began the same way, brightening unexpectedly, flickering, shedding gas, until their cores shattered into clouds of debris. C2025 R2's erratic behaviour fits that same pattern. But unlike the others, it was already near Earth's orbital region. The community started watching closely. Observatories in Chile, Spain and Australia began nightly imaging campaigns tracking its expansion. Amateur astronomers reported changes in brightness, noting irregular intervals of fading and flaring. The pattern was irregular, suggesting not rotation, but stress. By October's first week, the evidence was clear. This comet wasn't just venting, it was disintegrating. And that realization shifted attention to its path, because while its nucleus posed no threat, the dust and fragments it released could. Earth would pass just 0.2606 astronomical units, about 39 million kilometres, from its trajectory on October 20th. Close enough that even small debris trails could pose risks to spacecraft and satellites if dense dust streams form. But before those risk assessments could even begin, astronomers needed to understand what was breaking apart and why it wasn't seen until now. That search for answers led to a question far stranger than expected. What exactly happened when R2 passed the Sun, unseen and unrecorded? It's the missing day, the 24 hours that no one saw. When C2025 R2 swept past the Sun at just half an astronomical unit, every instrument designed to monitor such encounters was effectively blind. The comet's brightest, most violent moment unfolded behind the solar glare, where its nucleus endured the full heat of solar radiation and survived. Barely. What happened during that window remains one of the most critical and most uncertain parts of the entire event. Perihelion is the moment a comet faces its trial. The Sun's energy doesn't just warm it, it attacks it. Surface ices sublimate explosively, releasing trapped gases, dust, and complex organics. Jets burst through weak crusts, sometimes splitting the nucleus apart. For many comets, perihelion is the end. But R2 emerged, altered and unstable, suggesting something inside it had changed. The first post-perihelion data hinted at that violence. When SWAN detected its hydrogen cloud on September 11th, the amount of outgassing indicated that the comet had been boiling at perihelion. If 40 kilograms of water were escaping per second afterward, the peak rate near the Sun must have been several times higher, potentially hundreds of kilograms per second. That level of activity would have transformed the comet's structure. Models suggest that such an outflow exerts recoil forces comparable to weak gravity on small bodies. In R2's case, those forces were uneven, acting like miniature rocket engines firing randomly across its surface. The result? Non-gravitational drift, the same anomaly now complicating its orbit. But the chemical data made the story even stranger. Spectroscopy revealed not just the usual water and carbon compounds, but traces of cyanide, nickel, and an unusually low ratio of iron to other metals. Normally, comets contain both in abundance. The absence of iron suggests either selective loss, meaning parts of the surface were stripped away, or a primordial composition that's unlike typical Oort cloud objects. That deviation caught attention because it echoed something else: the composition anomalies observed in interstellar visitor 3I Atlas months earlier. Both bodies showed signatures of complex metal compounds behaving in unexpected ways under solar heating. But in R2's case, the effect was magnified, perhaps a sign of internal layering or trapped volatile pockets reaching critical pressure near the Sun. Astronomers reconstructed possible scenarios for what happened during those unseen hours. The most likely, a major outburst event during perihelion. As R2 heated, subsurface ice pockets burst, venting massive plumes of gas and ejecting fine dust at high velocity. Some of that material would have formed temporary jets, shaping its coma and shifting its trajectory slightly outward. If any fragments were expelled, they would now be following behind, invisible, faint, but potentially numerous. This explains the sudden post-perihelion brightening seen days later. As fresh ice was exposed, sunlight ignited new bursts of sublimation. Each surge pushed the nucleus slightly, altering its spin and perhaps fracturing it further. The evidence lies in its photometric curve, a rhythm of flares and fades, characteristic of unstable rotation. But the most haunting aspect of the perihelion pass is what we didn't see. We have no images, no spectra, no light curve from the moment of closest approach. There's only inference, a reconstruction from what followed. For a discovery of this magnitude, that's almost unthinkable. The data gap isn't just a scientific loss, it's a systemic one. This wasn't a hidden fragment or a tiny rock, this was a kilometre-scale object, and it managed to pass half the Earth-Sun distance without a single pre-perihelion detection. That's not an observational oversight, it's a structural blind spot in planetary defence. For context, Comet C 2019-Y4, Atlas, was detected 5 months before its own breakup in 2020. C 2025-R2 was found 1 day after perihelion. That's a reduction in lead time of over 150 days. If the geometry had been slightly different, if the object's trajectory had shifted earthward, we would have had no chance of early warning. This realization unsettled mission planners, because while a comet at 0.26 astronomical units isn't dangerous, a debris field could be. The Solar and Heliospheric Observatory can only detect large hydrogen envelopes, not dense clumps of rock or dust. Those fragments, invisible in ultraviolet, could remain untracked until they intersect orbital paths. That's why teams at NASA's Meteoroid Environment Office began analysing dust density models based on R2's activity. Even if just 0.1% of its expelled mass condensed into millimetre-scale grains, the resulting debris stream could pose risk to satellites or probes operating beyond Earth's magnetosphere, especially those near the Lagrange points. And still, questions linger. Did the nucleus fragment? Did it shed pieces now trailing behind? Did it alter its rotation period during the outburst? Without direct perihelion imagery, none of these can be answered yet, but every observation since points toward increasing instability. In the days following its solar encounter, R2 didn't fade as predicted. Instead, its coma thickened, expanding and glowing a vivid emerald hue. Amateur telescopes captured a diffuse halo nearly 300,000 kilometers wide, large enough to engulf Earth twice. That kind of sustained activity suggests that fresh material from deep beneath the surface had been exposed, feeding the outgassing cycle anew. Perihelion, then, wasn't just a passage, it was a transformation. Whatever emerged on the other side of the Sun wasn't the same object that entered. Its internal structure, spin state, and mass balance had all shifted. It became, in effect, a new comet, one now behaving in unpredictable ways as it moves closer to Earth's orbital corridor. And those unpredictable behaviours soon reached a peak no one could explain. Because as it moved farther from the Sun, when most comets quiet down, this one erupted again, brighter than before. It was late September, nearly 2 weeks after perihelion, when observers in Chile noticed a sudden jump in brightness from C2025R2. The comet's apparent magnitude increased by nearly 2.5 in less than 12 hours. In astronomical terms, that's an explosion. A quiet blur on one night transformed into a glowing sphere the next, expanding, pulsing, and radiating a strange green hue through the dawn sky. What caused it is still debated. Outbursts of this magnitude are rare after perihelion. Normally, a comet's energy fades as it recedes from the Sun, but R2 was behaving in reverse, becoming more violent as it moved outward. That's a physical contradiction, and it forced scientists to consider what could drive such a surge when sunlight was already weakening. The working theory involves pressure, not from outside, but from within. During perihelion, solar heat can penetrate deep into the nucleus, creating expanding pockets of vapour trapped beneath dust and crust layers. As the comet cools and contracts, those pressurized cavities can rupture, triggering delayed eruptions hours or days later. If this was the case, then R2's outbursts were echoes of its unseen solar trauma, each one a burst of memory, releasing what had been buried. But there's another possibility: fragmentation. When comets begin to fracture, their exposed surfaces multiply, producing more jets, more outgassing, and more reflected light. The light curve spikes because the object effectively increases its surface area. That's what astronomers feared they were witnessing, not a single nucleus, but the beginning of several. High-resolution imagery soon supported that suspicion. The Las Campanas Observatory captured fainter symmetries in the coma, uneven brightness, swirling structures, and streaks that hinted at multiple active vents. The jets didn't align. They seemed chaotic, firing from different axes, suggesting the nucleus was tumbling. That tumbling motion could explain the irregular light pattern observed in early October. Rapid brightening followed by sudden dimming, repeating over variable intervals. A stable comet rotates predictably, an unstable one doesn't. R2's rotation period remains uncertain, but the erratic flares suggest a body either breaking apart or wobbling under uneven thrust. Spectroscopic readings added more intrigue. The outburst released an abundance of CN, cyanide radicals, C2, and traces of NH2, classic signatures of volatile-rich material being freshly exposed. Yet there was something missing, almost no sodium emission lines, which are common in near-Sun comets. That absence might indicate that R2's surface sodium had already been vaporized during perihelion, meaning we were now witnessing deeper layers of the nucleus venting their contents for the first time. The colour shift in the coma, from pale green to a deeper emerald with blue fringes, also told a story. As more diatomic carbon and cyanogen flooded the coma, the wavelengths intensified. Photons from the Sun excited those molecules, producing the eerie spectral glow that observers described as breathing light. To the naked eye through a telescope, it looked alive, pulsing softly, expanding outward like a heartbeat. That heartbeat continued through early October. By the 3rd, the coma's diameter had doubled again. Ground-based images measured it at over 400,000 kilometers, larger than Jupiter. Yet despite its size, no one could clearly see the nucleus. Even the 2-meter telescopes in La Palma and Mauna Kea recorded only a bright core enveloped in haze. The nucleus remained unresolved, hidden behind a veil of dust and vapor. That raised a worrying possibility. If the nucleus could not be resolved, it might not be intact. Astronomers began to model what would happen if the comet had already fragmented. A split into 2 or more major pieces could account for the irregular jets, the unstable light curve, and the non-gravitational drift recorded in orbital solutions. If confirmed, that would mean R2 was no longer one object, but a small swarm. observatories coordinated to test that idea. On October 6th, the Lowell Discovery Telescope detected a faint linear streak trailing the main nucleus, possibly a dust streamer or debris arc. 2 nights later, amateur observers in Namibia reported a secondary condensation, fainter and offset, though atmospheric distortion left the measurement uncertain. Still, the reports matched what models predicted, the beginnings of a separation. Each new outburst strengthened the case. A fresh spike in activity on October 8th showed the comet's brightness rising by another factor of 4, accompanied by enhanced cyanide emissions. But this time, the tail pattern shifted, bending slightly southward relative to the sun's direction. That's a classic signature of structural asymmetry, the shape change that occurs when fragments move independently under solar pressure. By mid-October, there was little doubt that C2025 R2 was unstable. Its light curve looked like a seismograph during an earthquake. One moment calm, the next in violent motion. The outbursts had become both predictable and chaotic. Predictable because they kept coming. Chaotic because no one could forecast when. The comet's physical appearance now matched its behaviour. Diffuse, swollen, distorted. The coma expanded faster than models could accommodate, suggesting massive quantities of gas and fine dust were being released into space. And with every release, the potential hazard multiplied. Not to Earth directly, but to the region Earth would soon occupy. Because in less than 2 weeks, our planet's orbit would cross the area the comet had recently passed through. Not the same spot in space, but close enough that any lingering debris or micrometeoroid stream could pose a threat. This is what NASA calls a post-perihelion dust corridor, a zone where recent outbursts leave behind clouds of particles on slightly different orbital arcs. Most disperse harmlessly, but if the comet fragmented, those arcs could overlap with Earth's environment by late October. For now, the official risk remains near zero. Yet the scenario is exactly how past surprises have occurred, a fragmenting comet shedding unseen debris until it intersects Earth's orbital path months later. The reality is simple. No one knows how much mass R2 has lost, or how much remains intact. Every outburst rewrites the model. And so the monitoring continues, with telescopes worldwide locked onto a ghostly flickering sphere that shouldn't still be this active. But the next step in the story wasn't brightness, it was mystery. Because as the coma grew, the one thing everyone expected to find never appeared. No nucleus, no solid centre, no visible core at all. By October 10th, the global network of observatories had turned its collective gaze toward a single question. What exactly is at the centre of C2025 R2? Despite hundreds of images from telescopes around the world, and even space-based assets like SOHO and the Solar Orbiter, no one had been able to resolve a definite core. Every exposure, no matter how long, showed only a smooth, blinding sphere of light. No point source, no shadow, no visible rotation pattern. It was as if the comet had no solid heart at all. At first, this was written off as a limitation of optics. After all, the comet was surrounded by a coma hundreds of thousands of kilometers wide. But the issue persisted even in filtered infrared and radar attempts, which should have pierced the haze. The nucleus remained hidden, or worse, missing. That absence left 2 competing interpretations. The first, conservative one. The nucleus was simply small and buried beneath dense dust. A kilometre-sized icy body covered by a thick, optically opaque mantle of gas and debris. In that case, it was invisible only because it was overwhelmed by its own atmosphere. The second possibility was far more troubling, that the nucleus had already fragmented into smaller pieces, each too small to resolve individually. In this scenario, what we were seeing wasn't a single object at all, but a glowing swarm of icy shards moving together under their shared cloud. The photometric data pointed toward the latter. When researchers plotted the light intensity from the coma over time, the curve refused to flatten. Normally, a comet stabilizes once the nucleus reorients and its activity reaches equilibrium. But R2's luminosity kept fluctuating unpredictably, dimming, then flaring again, then fading without any apparent correlation to solar distance. That kind of erratic flicker suggests multiple, asynchronous sources of light. In other words, more than one active body. The Hubble Space Telescope, though not specifically tasked with tracking R2, was used in a brief parallel observation window on October 12th. The results, though preliminary, deepened the mystery. The images showed faint substructures in the inner coma, curved arcs, striations, and radial filaments that didn't align with any known jet model. Some appeared to move independently over time, consistent with the slow drift of detached fragments through a shared dust envelope. Astronomers described it as a self-contained storm, a cloud of material rotating and expanding like an organism breaking apart in slow motion. The colour gradient supported that interpretation. Near the centre, the green hue intensified, but toward the edges, a faint bluish halo appeared, produced by ionised carbon monoxide. That gradient forms when new gas is being vented from multiple small sources rather than a single nucleus. It was another hint that the comet was no longer whole. Still, the possibility of a hidden intact core couldn't be dismissed. If one remained, it would likely be dark, covered in carbon-rich residue, and masked by constant outflow. Such a surface would absorb nearly all instant light, rendering it effectively invisible. Some researchers compared it to Comet Borrelli's nucleus, a jet-black shape with an albedo lower than asphalt. But even then, R2's coma should have revealed subtle motion signatures tied to a rotating body. None were seen. And that silence, that absence of rotational periodicity, became its own data point. The European Southern Observatory reported that the inner coma showed no measurable periodic modulation. That meant either the object wasn't spinning measurably, or it was spinning chaotically, its fragments rotating independently. Meanwhile, dynamical models showed increasing non-gravitational acceleration. The comet's trajectory continued to shift by measurable degrees, implying sustained asymmetric thrust. In simple terms, it was still venting unevenly, changing its own orbit day by day. That's something only a highly unstable or fragmented object can do. If there was a nucleus, it was no longer controlling the structure around it. The tail, the jets, the coma, they were all drifting slightly off-axis, like a vehicle losing its centre of gravity. That made trajectory predictions difficult. Each new observation required recalculating orbital elements. Perihelion time, eccentricity, argument of perihelion, because small thrusts were constantly altering the path. Even with daily updates, uncertainty intervals were widening. NASA's orbit modelers used the term propulsive instability. It's not propulsion in the technological sense, but in effect, it behaves the same way. Gas vents act as tiny thrusters, introducing random velocity components. Over days or weeks, those components accumulate, sending the body onto a subtly new course. For spacecraft planners, this behavior is critical. The difference between a well-behaved comet and one undergoing non-gravitational drift can mean millions of kilometers of positional error after just a few weeks. But here's the deeper implication. If C2025R2 truly lost its nucleus, the outgassing would eventually subside. Once the fragments cooled, the emissions would fade and the object would disperse into a trail of dust. That's how many comets end, not with a collision or a dramatic explosion, but by simply dissolving into the solar wind. Yet that wasn't what was happening. Instead of fading, R2's hydrogen envelope continued to grow. The comet seemed to be sustaining itself, as though fresh, volatile material kept being exposed at new depths. The object wasn't dying, it was evolving. That paradox turned R2 from an astronomical curiosity into a case study in failure. Not the comet's failure, ours. Because for all our telescopes and models, the simplest question remained unanswered. What exactly is the object we're observing? A fragment swarm? A disintegrating nucleus? Or something structurally different from any comet we've seen? Whatever it wasn't finished changing. Because as it approached its closest distance to Earth, its physical instability began to manifest in its motion. Its orbit no longer fit standard models. It was moving under forces we couldn't fully predict. By October 13th, orbital analysts were staring at numbers that didn't add up. C2025R2's predicted position and its observed position were diverging, not dramatically, but persistently. At first, it was a few arc-seconds. Then, over several days, the difference grew into measurable space. Tens of thousands of kilometers off the modelled track. This wasn't an error in observation. It was a physical shift. Something was pushing the comet. That something was invisible but unmistakable. The jets! When volatile gases escape from the sunlit side of a comet, they act like tiny thrusters, each venting mass and exerting an equal and opposite force on the nucleus. Normally, these thrusts average out as the body rotates, but C2025R2 was anything but normal. Its chaotic tumbling and asymmetric activity meant some vents fired longer, stronger, or at unpredictable angles. The result was a constant, irregular push, small but cumulative. This phenomenon, known as non-gravitational acceleration, isn't rare among comets, but in R2's case, it's unusually intense. Observers at the Jet Propulsion Laboratory measured an acceleration parameter almost 5 times higher than typical for comets of similar size. That placed R2 among the most dynamically unstable long-period comets ever recorded. It was moving as if it were alive, adjusting its course not by impact or gravity, but by the uneven exhalations of its own volatile body. The first clue came from the changing shape of its coma. High-resolution imaging from La Palma showed faint fans and spikes radiating from the nucleus region, consistent with multiple gas jets firing at oblique angles. These plumes would appear, twist and fade within hours, implying the vents were active for short bursts before collapsing or relocating. Researchers modelled their orientation relative to solar input. The data suggested the comet wasn't spinning smoothly, but rather in a complex precession, a wobble that changed its sunlit zones unpredictably. Each new orientation activated different vents, altering thrust direction and pushing the body along a slowly drifting course. By mid-October, that drift became quantifiable. The orbital solution had to be revised daily. Each update shortened the comet's perihelion timing and slightly adjusted its trajectory angle. The result was a slow, steady migration of its projected path, not toward Earth, but tangibly away from its initial predictions. The drift wasn't dangerous, but it was revealing. It showed that R2's internal dynamics were still active and unpredictable, a kind of physical feedback loop between its surface and its orbit. And here's the curious part. The jets didn't behave like simple water vapor eruptions. Spectroscopic data from the Lowell and Subaru telescopes detected significant emissions of carbon monoxide, CO, and carbon dioxide, CO2, volatile compounds that sublimate at much lower temperatures than water ice. This meant that the outgassing wasn't being driven solely by solar heat. It was happening even in shaded or cooling regions. That's an indicator of deep fractures, conduits reaching into the nucleus, venting material from layers untouched by sunlight. In other words, the comet was leaking from within. These internal leaks create irregular impulses, tiny continuous nudges that act over hours or days. Multiply that across multiple jets, and you get measurable orbital deviation. The pattern was chaotic enough that even the most refined dynamical models struggled to predict where R2 would be a week later. This jet drift also hinted at instability in rotation. When gas escapes unevenly, it can torque the nucleus, changing its spin rate. For C2025R2, the inferred torque exceeded that of many known comets, suggesting a risk of structural breakup if the body couldn't dissipate the stress. The parallels with other unstable comets were hard to ignore. Comet 67P, visited by ESA's Rosetta mission, displayed similar jet-induced shifts, but its shape and rotation were well mapped, allowing for correction. Comet C 2019. 4. Atlas exhibited rapid drift just before its total disintegration, and the interstellar visitor, 2E Borisov, also showed a symmetric thrust as it shed volatile material far from the Sun. C 2025R2 joined that same pattern, only this time its behaviour was unfolding within Earth's neighbourhood at a mere 0.26 astronomical units distance. The implications stretched beyond astronomy. For satellite operators and agencies managing deep space probes, even minor deviations could matter. The comet's expanding gas and dust environment could intersect solar wind streams, injecting unpredictable turbulence into regions crossed by spacecraft signals. The European Space Operations Centre, ESOC, issued internal advisories for missions using solar observatories near the ecliptic, urging recalculated shielding alignments for October 20th to 25th. None of this meant Earth was in danger, but it illustrated how a drifting, fragmenting object can ripple through technological space. A comet's orbit isn't just a line, it's a living corridor of debris, plasma and radiation scattering outward with every jet. By October 15th, analysts began describing R2 as a self-propelling system. Not intentional, of course, but reactive, organic, erratic. It was writing its own trajectory in real time, The irony wasn't lost on the scientific community. While humanity celebrated its growing mastery of space navigation, a frozen relic from the Oort cloud, operating on nothing but physics and sunlight, was outmaneuvering every predictive model we had. And the closer it came to Earth's orbital corridor, the clearer it became that the comet's greatest danger wasn't impact at all, it was what it was leaving behind. By October 16th, the numbers were locked in. C 2025 R2 would pass 0.2606 astronomical units from Earth, about 39 million kilometers, on October 20th. Astronomically speaking, that's safe, comfortably distant. Yet for mission planners, satellite operators and scientists, it wasn't the distance that mattered. It was the uncertainty around what would come with it. Because comets don't travel alone. Every outburst, every jet, every microscopic grain it sheds becomes part of a diffuse cloud that stretches millions of kilometers across. For weeks now, R2 had been erupting, violently, erratically, and no one could say exactly how dense its debris field had become. At closest approach, Earth and the comet wouldn't share the same position in space, but they'd share the same region, a corridor of dust, ice, and gas expanding outward from the Sun. Even if 99% of that material dissipated harmlessly, the remainder could still graze through Earth's orbital path days or weeks later. The real concern wasn't for people, it was for machines. Orbiting satellites, deep space probes, even the James Webb Space Telescope sitting far beyond the Moon's orbit, all of them operate in or near regions that can be affected by microscopic debris streams. A particle no larger than a grain of sand moving at 60 kilometers per second carries the kinetic energy of a rifle shot. Multiply that by billions, and you have a fine mist of potential shrapnel invisible to radar, impossible to deflect. This is what NASA refers to as a micrometeoroid environment. Normally it's predictable, a steady background drizzle of dust from long dispersed comet tails. But when a new, active comet crosses near Earth's orbit, those models falter. A sudden outburst can seed new streams of debris on short notice. That's what R2 was now suspected of doing. The European Space Operations Centre began quietly recalculating orbital alignments for key missions. The Solar and Heliospheric Observatory, ironically the same spacecraft that had discovered R2, was projected to pass through a slightly denser dust corridor in early November, as the comet's tail intersected the L1 region. It wasn't dangerous yet, but it required monitoring. Even low Earth orbit systems were being considered. Most cometary dust burns up high in the atmosphere, harmlessly producing meteors. But when a large active comet passes nearby, the upper atmosphere can temporarily enrich in ionized particles, affecting radio transmissions and radar propagation. Those effects are subtle. Seconds of interference, microbursts of static. But for defense and communication systems, even those seconds matter. Still, the scientific curiosity outweighed the concern. This was an unprecedented opportunity. A major newly discovered comet, actively fragmenting, passing within the range of Earth-based sensors. Observatories mobilized globally to capture it in every wavelength. Optical, infrared, ultraviolet, even radar scatter. The goal wasn't just to study R2, but to learn how it hid. Because R2 had arrived unannounced from a blind direction, detected only after its solar encounter. That alone made it a case study in the vulnerabilities of planetary surveillance, and now it was providing a natural laboratory for understanding how such bodies evolve once discovered too late. The days leading up to October 20th were tense and electrifying. Astronomers from the Virtual Telescope project streamed live views online, showing a diffuse glowing sphere drifting silently across the night sky. It wasn't bright enough to see without aid, but through the instruments, its beauty was undeniable. A green orb wrapped in faint ribbons of gas, its tail subtle, its motion steady. To most of the world it was invisible, to those watching it was mesmerizing. As the comet approached, photometric measurements confirmed what many had suspected. R2's brightness variations were slowing. The outbursts were less frequent, the light curves smoothing slightly. It wasn't stabilizing, just exhausting its fuel. The wild venting that had carried it across the inner solar system was winding down. But even as the light settled, the motion did not. The latest JPL orbital refinement released on October 18th showed a continuing drift, a deviation of approximately 20,000 kilometers from the predicted ephemeris. Again, not toward Earth, but off the model entirely. the comet was still subtly accelerating, guided by its own fading jets. That unpredictable motion created a second-order problem: uncertainty in the debris path. When the nucleus shifts, the dust trails it leaves behind shift too. That means models predicting where the tail would move and whether it might intersect Earth's orbit became less certain with every passing day. In simple terms, the more R2 changed, the less anyone could say about what came next. Yet there was one thing all analysts agreed on: even with its fading activity, the comet was producing enormous quantities of microparticles. Calculations from infrared scattering data estimated over 1 billion kilograms of dust had been released since perihelion, enough to fill a small mountain. Most of that material would disperse harmlessly, but a fraction could remain coherent, forming streams that would orbit the Sun for centuries. In time, those streams could evolve into meteor showers, faint reminders of the night a hidden object slipped through the Sun's glare. For now, though, the focus was immediate. As October 20th drew near, deep space networks prepared to monitor any anomalies in communication signals, a precautionary measure whenever a new active comet passes near Earth's orbital zone. There would be no collision, no spectacle, no end-of-the-world moment. But for the scientists watching, the event was still historic, because every data point gathered now, every fluctuation in light, every shift in path, would help rewrite the models that failed to catch R2 in the first place. This was the test case for how a modern detection system reacts when the unknown arrives unannounced, and it was about to reveal a truth that went beyond this one comet, a truth about what hides in the spaces we cannot see. It's easy to imagine danger as something solid, a rock, a body, a collision. But in space, the true hazards are often invisible. C2025 R2 is not on a collision course with Earth. Its trajectory is well clear. Yet its presence is stirring concern for reasons most people never think about, the kind of quiet, invisible risks that orbit above us every day. The threat isn't impact, it's the debris field. Every comet leaves one, an expanding corridor of microscopic dust, gravel, and vaporized material stretching for millions of kilometers along its orbit. With R2, the scale is unprecedented. Its violent outbursts, its fragmentation, its unresolved nucleus, all point to immense material loss. And that material, once ejected, doesn't vanish. It lingers, it drifts, it spreads through the inner solar system like faint smoke on a cosmic wind. When Earth passes near that residue, even at distances of tens of millions of kilometers, it can encounter invisible fragments moving at extraordinary speeds. Most burn up in the atmosphere, producing no more than a whisper of light. But some remain aloft, striking satellites, solar arrays, or spacecraft at velocities up to 70 kilometers per second. At that speed, a particle the size of a paint chip carries the energy of a bullet. A grain of sand becomes shrapnel. A pebble becomes a bomb. This is the invisible threat. Not a cataclysmic strike, but cumulative attrition, the steady erosion of humanity's fragile technology orbiting Earth. NASA's Meteoroid Environment Office has models for this. They simulate how cometary debris disperses over time. Normally these models are stable. They rely on predictable outgassing rates and known orbital paths. But R2 broke both assumptions. Its jets distorted its orbit. Its fragmentation created unknown streams. The result is uncertainty, not just in its path, but in the distribution of the debris it left behind. Some of those streams may never intersect Earth's orbit. Others might, months or even years from now. The danger isn't immediate, it's systemic, because R2 exposed how blind our early warning systems still are to evolving particulate environments. Satellites are designed to handle micrometeoroid strikes. Panels can withstand hits from dust less than a millimeter across. But denser streams, like those produced when a comet breaks apart, can saturate orbital regions with far higher flux than usual. For a few hours or days, the odds of a damaging impact rise exponentially. It's rare, but it's not theoretical. In 2022, NASA's James Webb Space Telescope sustained a micrometeoroid strike that slightly deformed one of its primary mirrors. The culprit, a random particle, likely from a faint debris stream tied to an old comet long forgotten. That was one speck, one chance encounter. Now, with R2, astronomers are watching the formation of a new, potential source in real time. And this time they're watching late. Because by the time R2 was discovered, it had already passed perihelion, already ejected the bulk of its material. The dense, sunward-directed streams it produced during that unseen phase have already spread into heliocentric space. We didn't see them form. We can only infer their existence from the comet's instability. This is what's known as a data latency event. When discovery lags behind action, mitigation becomes impossible. You can't shield satellites from dust you don't know exists. You can't model streams you didn't detect forming. You can only react afterward, when signals drop, when telemetry degrades, when impacts are logged. That's the haunting realization behind C2025R2. It's not just an object that slipped through the system, it's a demonstration of how modern detection still fails to keep pace with real-time events. Even now, weeks after discovery, global observatories are still playing catch-up, mapping its dust tail, estimating particle size distributions, refining reflectivity models. But without pre-perihelion data, every calculation begins with uncertainty. And yet this isn't just about one comet, it's about what the next one will do. R2's discovery is part of a growing pattern, a series of near-Sun objects emerging suddenly, seen only by solar monitoring spacecraft. The most famous example is 2002-06, which appeared from the same blind corridor, unannounced and fragmented days later. Then came 2018 V1, appearing from the daylight side, then 2021-01 Leonard, barely caught in time. Each case underscores the same weakness. The region near the Sun, the sunward zone, remains largely unmonitored. And that's precisely where R2 came from. In a way, it's poetic. The Sun, the source of all illumination, also hides what threatens us most effectively. Its glare blinds our instruments, its radiation drowns our signals. Anything approaching from that direction can arrive undetected until it's already too close to study. If a comet can cross that invisible threshold undetected, so can anything else. A large asteroid, a fragment swarm, even an artificial object gone rogue. That's the fear that lingers now among astronomers and planetary defense experts. Not that R2 will hit us, but that something else could one day using the same hidden corridor. C2025R2 was, in many ways, the warning shot. Not a weapon, not an impactor, but a messenger. It revealed a flaw not in our skies, but in our vigilance. And that's why, as its faint green glow drifts away into the outer solar system, the focus is already shifting, away from the comet itself, toward the system that failed to see it coming. This isn't the first time an object has slipped past us. Every few decades the same story repeats. An unseen visitor appears suddenly, too late for full study, too close for comfort. We tell ourselves the systems are improving, the surveillance denser, the sky safer, yet each generation meets its own R2. In 1843, before the modern telescope age, astronomers were startled by a blinding apparition near the Sun, the Great March Comet. It had come from nowhere, undetected until it flared into view, passing dangerously close to Earth's orbit. Its tail stretched across half the sky. For weeks afterward, the world marvelled, and then forgot. No one could explain how such a vast object could go unseen until the last moment. More than a century later, in 1965, Comet Ikeya-Seki did the same. It passed within 0.007 astronomical units of the Sun, so close that it glowed in daylight, and had never been catalogued before. Its core survived the solar encounter but fractured days later, scattering fragments into multiple tails. In the 1990s, SOHO began to detect sun grazers, almost weekly, most of them tiny, but the larger ones, like Comet Lovejoy in 2011, repeated the same story, discovered only hours before perihelion. And then, in 2013, a smaller event served as a reminder that size isn't safety. The Chelyabinsk meteor, a 20-meter fragment, entered Earth's atmosphere from the Sun's direction, completely undetected. It exploded over Russia with the force of 30 Hiroshima bombs, shattering windows across 6 cities. It was not the largest object of its kind, only the most unlucky. Its invisibility was the key. The Sun had hidden it perfectly. Now, in 2025, the pattern continues. C2025R2 arrived from the same sunward void, untracked, unannounced, revealed only after its closest solar pass. It's larger, slower, and harmless, but the parallel is unmistakable. History keeps circling back to the same blind spot. What's most striking is how these events always expose the same human tendency: confidence followed by surprise. After 2013, nations pledged new early warning systems. After 2020, when C2019Y4, Atlas, shattered unexpectedly, models were upgraded. After 3I Atlas's discovery in 2025, the world congratulated itself for its readiness. Yet within months, R2 appeared, unseen. The lesson isn't about technology, it's about assumptions. Each breakthrough convinces us the sky's accounted for, yet every hidden arrival proves how little of it truly is. Scientists call it the sunward exclusion zone, the area of space within roughly 15 to 20 degrees of the sun where ground-based telescopes cannot look without optical damage. It's a permanent void in coverage, and every object approaching from that direction can remain invisible until it passes beyond it. In 1843 it was a curiosity, in 1965 an inconvenience, in 2013 a wake-up call. And now, with R2, it's an indictment of complacency. Modern surveys like Pan-STARRS, Catalina and ATLAS cover the entire night sky every few nights, but night is the key word. Their sensors cannot operate during daylight or at low solar elongations. Infrared satellites like NEWISE extend coverage slightly closer to the sun, yet even they must protect their instruments from direct solar radiation. The result? A permanent observational gap, a blind hemisphere just beyond sunrise and sunset. That's where C2025R2 came from. The same region that produced Ikea-Seki, the same vector that hid the Chelyabinsk meteor. It's not just a blind spot, it's a historical pattern, an orbiting vulnerability. And there's another echo in history worth noting: fragmentation. Every major late-detected comet that exhibited violent outbursts went on to disintegrate. C1999 S4 Linear, C2012 S1 Eson, and C2019 Me4 Atlas all broke apart within weeks of perihelion. The process is so consistent that astronomers now speak of it as a thermal cascade. Once volatile jets begin to dominate a comet's motion, the internal structure begins to fail. C2025. R2 now fits that profile perfectly. Delayed discovery, violent activity, drifting orbit, unresolved nucleus. If history holds true, fragmentation is either imminent or already underway, and fragmentation carries its own legacy. When a comet breaks apart, its pieces remain in orbit, spreading along the original trajectory. Over time, they form meteor streams, invisible rivers of debris that Earth occasionally crosses. The annual Perseid and Leonid showers, among the most beautiful spectacles in the sky, are the remnants of such disintegrations. It's poetic in a way. What begins as danger ends as wonder. But before wonder comes risk. For each new comet that crumbles, fragments can remain on crossing paths for centuries. If C2025R2 follows the same path, its remnants will linger long after its glow fades. New, invisible trails threading through the solar system, unseen but persistent. This, then, is what historical echoes really means. Each discovery isn't isolated. It's part of an ongoing story, of what we miss, of what hides, of what returns. And with R2, the story is still unfolding, because every echo points to the same underlying cause, the same structural flaw in how we watch the sky. And as the comet fades into darkness, the next chapter turns not to space itself, but to the system watching it. In theory, the planet is always watching. Hundreds of telescopes sweep the sky each night. Automated surveys compare frames pixel by pixel against databases containing billions of known objects. Artificial intelligence filters noise, flags anomalies, and assigns provisional designations within minutes. The illusion is that the sky is covered, that nothing large can move unseen. C2025R2 proved that illusion false. The comet's late discovery wasn't a fluke of chance. It was the inevitable product of geometry, technology, and bureaucracy colliding. It revealed the quiet truth behind planetary defense. Our vigilance depends on where we look, when we look, and who decides it's worth looking. The surveillance gap is a simple phrase for a complex failure. It isn't just the sunward blind zone, though that's part of it. It's also the fragmentation of responsibility across dozens of agencies and institutions, each with their own data, their own thresholds, and their own priorities. When an object approaches from an unmonitored direction, the system relies on redundancy. But redundancy doesn't exist if every telescope assumes someone else is watching. R2 entered through that void, a region of daylight the ground can't penetrate, where no dedicated space-based sentinel currently stares. There are spacecraft that could see it, like SOHO or STEREO, but they weren't designed for real-time survey work. Their images are meant for solar physics, not planetary defense. The comet was visible in their data for nearly a day before its recognition. It simply wasn't anyone's job to notice. That delay, 24 hours between appearance and alert, is what changed the tone among professionals. Because in planetary terms, that's not a delay. That's a lifetime. The core of the problem is prioritization. The global detection network is optimized for near-Earth asteroids, fast-moving rocky objects that can impact the planet. Comets, especially long-period ones like R2, are treated as secondary. They're larger, brighter, and slower, but considered less dangerous because their orbits are predictable once known. The flaw in that logic is obvious. They aren't predictable until after they're found. That gap in philosophy, what counts as urgent, what doesn't, meant that when R2 approached, the algorithm didn't know to look for it. It wasn't in the nightly scans. It wasn't in the near-Earth alert protocols. It simply didn't exist until it was almost gone. And the danger of that mindset extends beyond this one event, because the same detection logic applies to every untracked object, natural or not, approaching from the solar direction. Several studies published after the 2013 Chelyabinsk incident warned of exactly this. The risk of sunward approaches, objects invisible to optical surveys because they move from the day side, was quantified, modelled, and documented. The solution was known too: launch a dedicated space-based survey telescope operating in infrared, positioned far enough from Earth to see into the sun-facing half of the sky. The proposal exists. It's called the NEO Surveyor Mission, designed to orbit near the L1 point and peer sunward in mid-infrared. But its funding, delayed for years, was only partially restored in 2024. Construction continues. Launch is scheduled for 2027. Until then, the blind spot remains. R2's emergence from that very region turned a theoretical vulnerability into a case study. It demonstrated that even with 21st century coverage, the system still fails where sunlight rules. But the surveillance gap isn't just physical, it's procedural. When SOHO's SWAN instrument flagged the hydrogen cloud on September 11th, the automated alert went into a classification queue. Cross-verification required human confirmation, and that confirmation had to wait for a review window. By the time a human saw the anomaly and recognized its motion, the comet had already passed perihelion. That's not negligence, it's process. Every detection passes through layers of validation to avoid false alarms, but those layers take time, and time is exactly what's missing when dealing with inbound bodies. The latency between observation, recognition, and classification is small in human terms, hours, but immense in celestial ones. In those hours, R2 moved millions of kilometers. It's a paradox of modern astronomy. We collect too much data to see what's urgent. In the past decade, sky surveys have generated petabytes of imagery, far beyond what analysts can review in real time. Machine learning filters have improved dramatically, but they still depend on training sets, on prior examples. They recognize what they've been taught to expect, and R2 was not something they expected. Its ultraviolet brightness, its lack of pre-discovery arc, its emergence near the solar limb, all characteristics outside normal parameters, so it slipped through. The surveillance gap is also temporal. Comets spend most of their lives invisible, distant, dark, inert. They awaken only when the sun's heat touches them, usually when they're already close. Detection, therefore, always lags behind activation. What R2 showed was that the lag can now reach zero, discovery after the event. That's the nightmare scenario planetary defense planners try to avoid. A late warning object on an Earth-crossing trajectory, discovered only after its closest approach. R2 wasn't dangerous, but it fit the geometry perfectly. Replace it with something smaller and faster, an asteroid tens of meters wide, and the story changes entirely. This is why the surveillance gap matters, because it isn't about the one we caught, it's about the one we won't. C2025-02 will fade into darkness soon, its orbit charted, its tail dispersing. But its legacy will remain as a policy question. How do we close the space between discovery and danger? And to answer that, astronomers are turning inward, not to the sky, but to the systems they've built. Because the next failure won't come from the stars, it'll come from the delays between detection and decision. In space, discovery is only the first step. What happens after discovery? How fast the data moves, who receives it, and how decisions are made determines whether the system works or fails. See 2025. R2 exposed that weakness not through danger, but through timing. It showed that bureaucracy, not blindness, may be the real threat. When SOHO's SWAN instrument recorded the ultraviolet flare on September 11th, the automated pipeline did exactly what it was programmed to do. It logged the event, compared it to solar background models, and sent it into a verification queue. But in that queue, everything pauses. Data analysts must review the imagery, cross-check with known artifacts, confirm motion across frames, and consult other instruments before classifying the signal as a new object. That review cycle usually takes 12 to 24 hours, an eternity when something is moving millions of kilometers a day. By the time C2025 R2 was confirmed as a comet and assigned a designation, it was already outbound. Its closest solar approach was history. Its peak activity had come and gone. The data delay didn't just cost time, it erased context. The same delay pattern exists across multiple institutions. NASA's Center for Near-Earth Object Studies, CNEOS, the Minor Planet Center, MPC, the European Space Agency's NEO Coordination Center, all work together under the International Asteroid Warning Network, AWN. But each has its own protocols. Each waits for confirmation before issuing alerts. False positives are costly, politically and publicly, so the system errs on the side of caution. It is cautious by design. That caution is what prevents panic, but it also guarantees latency. In the case of R2, it wasn't just one delay. It was a chain. SWAN's alert reached the MPC at 900 hours UTC. Preliminary orbit data wasn't processed until 1400 hours. Confirmation wasn't circulated until early September the 12th. The first public bulletin went out 12 hours after that, and only then did ground observatories begin targeting it for observation, more than a full day after perihelion. For an object discovered post-perihelion, that delay rendered the most valuable data, its reaction to solar heating, unrecoverable. The problem isn't incompetence, it's structure. Every detection system in use today was built for the age of nightly surveys, not continuous real-time monitoring. The bureaucracy around discovery assumes the sky is static, that hours don't matter. But for fast-moving or short-lived events, they do. Astronomers have a term for this: confirmation latency. It's the delay between the first photon captured and the moment the world knows what it means. R2 turned that term from theory into case study. The irony is that the technology to fix it already exists. Machine learning algorithms can cross-verify moving sources across instruments within minutes. Automated orbit solvers can project trajectories from a handful of data points. Satellites at L1 and L2 could feed real-time streams to cloud systems capable of flagging potential inbound bodies instantly. But implementing that network requires political will and budget. In 2023, a NASA ESA working group proposed an integrated sunward early warning system, combining data from solar observatories, heliophysics missions, and asteroid surveys into a single automated pipeline. The concept was simple: remove human delay from first contact. Let the network flag anomalies as soon as they appear, then route them directly to analysts. It was approved in principle, but never funded. Other priorities took precedence: climate missions, lunar logistics, Mars architecture. The blind spot remained. C2025 R2 reignited that conversation overnight. After its discovery, internal memos circulated between the US Planetary Defense Coordination Office and the European Space Operations Center. The tone was careful but clear. The system had worked, technically, but too slowly to matter. It was the Chelyabinsk problem, repeated at a higher altitude. The policy implications extend far beyond astronomy. Planetary defense is one of the few scientific fields where time equates directly to safety. Every minute shaved off detection to confirmation time compounds into hours of potential response. For a harmless comet like R2, the stakes are low. For a small, inbound impactor, they're existential. And yet, every time an object like this appears, the same debate reignites: risk tolerance versus resource allocation. How much should humanity spend on watching a sky that rarely strikes? The answer, historically, has been just enough to notice, never enough to prevent. That calculus is shifting now. The events of 2025, 3, the Atlas, R2, and several smaller untracked objects that brushed Earth's orbit have begun reshaping that conversation inside space agencies. A new class of missions is being proposed, autonomous sky sentinels capable of operating in regions the Sun hides. Positioned near Mercury's orbit or even in polar solar trajectories, these sentinels would see what Earth cannot, the Sunward corridor where R2 came from. But approval takes years, funding takes longer, and as every scientist involved in R2's discovery knows, the universe doesn't wait for committee votes. The comet is already leaving, fading into the outer solar system, its tail stretching thin. Yet the policies it exposed linger, unresolved. The bottleneck isn't data, it's decision-making. The system can see faster than it can act. And while bureaucracies debate procedures, astronomers are already moving on, shifting their focus from governance to evidence, because somewhere behind R2 something might be following. Fragmentation leaves more than dust, it leaves company. By mid-October, as C2025 R2 drifted away from the Sun, attention shifted from the comet itself to what might be trailing behind it. If its nucleus had indeed fractured, as every indicator suggested, then the space between it and the Sun might already be littered with smaller, fainter remnants. Detecting them would mean confirming fragmentation. Missing them would mean flying blind through a corridor of debris. The search began quietly. The first to act were the teams at the European Southern Observatory and the Lowell Discovery Telescope. Using wide-field imaging arrays, they began nightly deep exposures of the region just behind the comet's path, stacking hundreds of frames to hunt for faint, co-moving points of light. Nothing appeared at first. The field was noisy. Solar background, scattered dust, cosmic rays. But faint anomalies began to emerge by October 13th. Diffuse specks following the comet's velocity vector, each one barely visible above the background glow. They weren't confirmed fragments, not yet, but they were enough to trigger the Fragment Watch protocol. This procedure, developed after the disintegration of Comet C 2019Y4 Atlas, involves coordinating observations across multiple hemispheres. Telescopes in Hawaii, Chile, South Africa, and the Canary Islands take sequential exposures from different angles. If an object appears in all images at consistent relative motion, it's confirmed as a discrete fragment. By October 15th, two candidates met that criterion. They were faint, magnitude 18 and 19, roughly 1,000 times dimmer than the main body. Both trailed slightly behind the primary nucleus, separated by about 30,000 kilometers, moving in near-identical orbits. They weren't reflections, they weren't noise, they were pieces. At first, excitement dominated. Confirmed fragmentation means valuable science, a chance to study the physics of comet breakups in real time. But beneath the scientific thrill was unease, because fragmenting comets don't stabilize. Once they begin to split, the process accelerates. Internal pressure, rotation, and thermal stress keep tearing them apart. What begins as 2 fragments becomes 10, then 100, then a diffuse stream of rubble spreading invisibly through the inner solar system. For R2, the timing was critical. Earth's orbital path would pass within 0.26 astronomical units of the comet on October 20th, close enough that any secondary debris cloud, even faint, could intersect our space environment within weeks. That possibility mobilized a new set of observers, not astronomers, but engineers. The European Space Operations Centre, ESOC, requested updated dust density estimates for spacecraft operating near the ecliptic. NASA's Meteoroid Environment Office ran simulations assuming the confirmed fragments were shedding fine material. The results weren't alarming, but they weren't negligible either. The model suggested a temporary rise in micrometeoroid flux near Earth's orbit, a subtle, invisible reminder that the comet's story wasn't over. And the fragment count kept rising. By October 17th, a third condensation appeared, this one larger, perhaps tens of meters across. It wasn't bright enough to reflect much sunlight, but it registered clearly in near-infrared. That same night, astronomers from the Catalina Sky Survey detected a faint, elongated streak that might represent a diffuse debris plume. If so, R2's nucleus had begun to disintegrate more extensively than anyone realized. The images told a consistent story, a comet tearing itself apart silently, particle by particle. What made this fragmentation so difficult to study was geometry. The comet's trajectory, viewed from Earth, placed its tail nearly edge-on. That meant fragments aligned along our line of sight, blending into the coma's light. Detecting individual pieces required filtering techniques that could isolate motion vectors separated by fractions of a degree. The process was tedious, painstaking, but vital. Every confirmation mattered. Each fragment carried a record of the comet's internal structure, density, composition, tensile strength. Studying their brightness variations could reveal whether R2's breakup was thermal, rotational, or mechanical. So far, the pattern leaned toward rotational instability. That would fit the erratic outburst cycle observed in late September. As the nucleus spun faster under asymmetric jets, centrifugal stress exceeded the material's cohesion, and the comet began to split. If this interpretation holds, R2's fragmentation was inevitable. The outgassing that saved it from solar vaporization also destroyed it from within. By October 18th, fragments were being numbered. The Minor Planet Center catalogued 4 candidates under temporary designations R2A through R2D, pending confirmation. Each one appeared to follow the same orbit, with only slight velocity differences, the slow drift typical of breakup debris. Their faintness suggested small size, perhaps 100 meters at most, too small to detect earlier, too large to ignore now. And then came a surprise. Infrared analysis from the Neowise spacecraft detected elevated dust emission extending well beyond the visible coma, an extended fan stretching over 5 million kilometers behind the nucleus. The data hinted at a massive release of fine particles, possibly the result of a recent large-scale disintegration event. If correct, R2 had just shed another major section of itself, unseen, silent, and unrecorded. The fragment hunt shifted from confirmation to containment, estimating how much of the nucleus remained intact and whether further breakups were imminent. The answer? Likely, yes. Comets don't die instantly. They unravel. What we were seeing was the slow collapse of a body that had survived eons in darkness, now destroyed by a few weeks of sunlight. Yet within that collapse lay a scientific gift. Every fragment, every plume, every faint streamer of dust adds to our understanding of how comets evolve and how fragile they truly are. Still, the discovery carried a deeper implication. If R2 had fragmented this completely, its dust and debris wouldn't vanish quickly. They would persist, forming new streams that Earth will eventually cross. Maybe not now, maybe not next year, but soon. Each encounter would bring new meteor activity, faint traces of the comet's demise visible in the night sky. And when that happens, those streaks of light will be reminders, not of danger, but of failure. A failure to see sooner, to act faster, to coordinate better. That recognition is already reshaping how astronomers think about the future. Because R2's fragmentation isn't just a physical event, it's a policy catalyst. The question now isn't whether we can track such objects, it's whether we can track them in time. And for that, a new kind of system will be needed, one capable of looking directly into the sun's glare where the next one will hide. When C2025-R2 appeared in the solar glare, unseen until it was already past the sun, it wasn't just a comet slipping through a telescope's field of view, it was a failure of architecture. The event forced astronomers, engineers and policymakers alike to confront an uncomfortable truth. We are watching the wrong half of the sky. For decades, planetary defense programs have focused outward, surveying the night sky, mapping the darkness, and ignoring the daylight. Every major ground-based telescope, from Pan-STARRS in Hawaii to Atlas in Chile, is designed for darkness. The assumption has always been simple. What can't be seen near the sun isn't worth the risk. C2025-R2 shattered that assumption, because it didn't come from deep space where telescopes were pointed. It came from the bright side, the region facing the sun, the place no one watches because no one can. And in doing so, it illuminated the biggest vulnerability in our planetary awareness, the absence of dedicated sunward observatories. Astronomers call this region the solar blind cone, a wedge of about 30 degrees on either side of the sun where optical detection is effectively impossible from Earth. In that glowing void, the sun's brilliance drowns everything. Asteroids, comets, even large objects the size of mountains can travel undetected until they emerge days or hours before perihelion. R2 used that void as a cloak. Its discovery, one day after perihelion, came not from a telescope designed to guard us, but from a solar instrument, SOHO's SWAN, that stumbled upon it by accident. The comet's hydrogen cloud simply happened to overlap a field of ultraviolet imaging intended for heliophysics research. It was a coincidence, not a triumph of surveillance. That coincidence will not hold forever. And so, as R2 drifts outward into the cold, it has left behind a demand, a call for eyes where none exist. The push for sunward observation isn't new. Scientists have warned about it for years. After the 2013 Chelyabinsk event, the United Nations Office for Outer Space Affairs issued a recommendation for dayside object monitoring to detect inbound bodies approaching from the solar direction. But funding and technical challenges stalled every proposal. Infrared telescopes are expensive, shielding them from the sun's heat is complex, and for decades, the absence of a crisis made the cost hard to justify. Now, R2 has made that justification for them. Since its discovery, multiple agencies have revived dormant plans. NASA's NEO Surveyor, scheduled for launch in 2027, will operate in mid-infrared, capable of detecting objects approaching from the sun's direction. The European Space Agency is advancing Neomir, a similar mission designed to orbit near the L1 point, continuously scanning the sunward sky for infrared signatures. Both spacecraft will be equipped to see through glare to detect the faint thermal emissions of objects invisible to optical sensors. These missions are now no longer academic, they are priority. But the lesson of R2 extends beyond technology. It's about process, how data moves, how warnings are shared, how global coordination happens in real time. The comet's appearance exposed not just physical blind spots, but institutional ones. Data from solar observatories, asteroid surveys and space weather missions exist in silos, each analysed for different purposes. A hydrogen cloud that signals a comet might, in another database, be dismissed as noise. The call for eyes now means more than new telescopes. It means unification. A shared early warning framework connecting solar missions, planetary defence networks, and national space agencies into a single continuous watch. It means removing the distinction between solar observation and planetary protection, because, as R2 proved, the two are inseparable. There's a quiet movement within the astronomical community now. Scientists pushing for a permanent sunward monitoring network, a distributed system of small satellites placed in heliocentric orbits closer to the Sun, each scanning the forward-facing hemisphere invisible from Earth. Together, they would form a panoramic watchtower, the first true 360-degree shield around the planet. It's an ambitious vision, but history suggests it will take another near miss to make it real. Every major advance in planetary defense has followed a surprise. Tunguska led to impact awareness, Chelyabinsk led to global coordination. Now R2 may be the catalyst for sunward vigilance. Each event forces a step forward, each comet a reluctant teacher. The irony is that the danger isn't growing, our awareness is. Space has always been filled with wanderers like R2. We're only now realising how often they pass unseen. And as the comet fades, its fragments scattering into the darkness, the lesson remains painfully clear. Seeing the universe is not enough. We must also see the space the sun hides, because that's where the next warning will come from, and next time it might not be harmless. The final data from R2 will continue arriving for weeks. Radar returns, dust measurements, spectral readings. But even before the numbers are complete, the message is already written. This time we saw it late. Next time we might not see it at all. C 2025. R2 is fading now. Its coma, once a furious green storm, has thinned into a pale mist trailing quietly into the night. The fragments that once glowed fiercely under the sun's heat are dispersing, cooling, falling silent. In a few weeks, it will be gone. Another transient visitor returning to the dark between the stars. But the silence it leaves behind is not peaceful. It's reflective. This comet didn't arrive as a warning from space. It arrived as a mirror, showing us the blind spots in our vigilance, the fragility of our confidence, the distance between knowing and understanding. It revealed that our systems see everything except what hides in the light. R2 never threatened us physically, it never needed to. Its danger was metaphorical, a reminder that complacency is the most persistent force in the solar system. For all our technology, our telescopes, our algorithms, one cosmic wanderer slipped past unnoticed until it was already here. And that's the real story. Not that an object came close, but that we never saw it coming. When historians look back, they may not remember C2025, R2 as a comet at all. They'll remember it as the moment planetary defense stopped being theoretical, the moment we realized that sunlight itself, the very thing that reveals the universe, can also conceal it. Somewhere beyond Earth's orbit, the fragments continue to drift, carried by invisible solar winds. They'll spread across millions of kilometers, forming faint ribbons of dust that will, one day, brush past our world again. When they do, they'll burn in the atmosphere, quiet streaks of light across a night sky that we'll barely notice. But those streaks will mean something. They'll be the last visible traces of the day humanity was reminded how little of its sky it truly sees. C2025, R2 has moved on, but its shadow remains. Not on Earth, but on the way we watch it. Because the next one won't announce itself. It won't give us months of warning. It will emerge from the same glare, the same blind corridor, carrying the same silence. And when it does, everything we learned from R2, every delay, every oversight, every missing hour, will be tested again. The universe doesn't repeat its mistakes. It waits for us to repeat ours. And this time, the question isn't whether we'll see the next one coming, it's whether we'll see it in time.